Hello everyone, in this video we are going to be talking about basic concepts such as charge, current, voltage, power and energy, and they're really important throughout the course, so get ready for it. So the first one that we're going to investigate is charge. So let me put a title in here. What is charge? So actually you have a rough idea what charge is in general, but let me say that it is just a property of atomic particles. And I'm going to put that definition right here, and when I put the definition we will just speed up the video so you're not going to waste time. Nice. In the previous video, I have told you that the unit of charge is coulomb. That's also a really good information. But what else do we get to know about charge? So first of all, we know matters consist of atoms, right? And atoms are consisting of electrons, protons, and neutrons. So for a fact, from high school, we know protons do have a charge, which is in an amount of 1.6 times 10 to minus 19. That's pretty good, but this charge is positive. And of course, it is in the unit of coulomb. And what about electrons? Electrons are actually carrying exactly the same amount of charge, but the problem is this time the sign is different. It is negative. So from that, we can conclude charge can be positive or negative. This is really important. Positive or negative. These are the first information about charge. But the part that we are really interested in is when our charges flow. So what is that supposed to mean? Our charges, charge in general has one unique feature, which is that it is mobile. What is that supposed to mean? It can move, and this is really important. How can we make them move? It is really easy. When you connect a battery to a wire, then the charges flow. That's it. And when charges flow, something beautiful happens, which is that charges will be compelled to move, with the effect of the battery, and then we create current. That's really important. Let me put that in here. When charges flow, and let me put it this way, flow of charge is actually the reason why we are having current. And this is the relationship between charge and current. And since we're talking about a flow of charge, it must have a direction, right? So the direction is in this way. Imagine you are having a wire like this, all right? And then you are connecting that wire to a battery. So now we know for a fact charges are compelled to move, forced to move. That's why we're going to have some charges flowing around. So positive charges and negative charges are actually being together. So what is that supposed to mean? In a wire, we both have positive and negative charges. And when we think about it, some of them are positive and some of them are negative. So that means they will have different direction, and that is correct. So let's say the red arrow in here is representing positive charges, and also here we are going to have black arrow that is representing negative charges, and as you can see they have different directions. So one thing I want to mention in here is that we said flow of charge is the reason why we are having current. So when we have a flow of charge, then current occurs. But the question is, we have different types of charge, right? And when they flow in different directions since we both have positive and negative ones. But what about the direction of current? So that question is really easy. The direction of current is exactly in the same way of positive charges. So let me put that in here. So that's really nice, and since we're talking about current a little bit, let's define our second concept, which is current. So current is nothing but the rate of change of charge. Let me put that. And the unit for current is amperes that we have seen in the previous lecture. So one thing in here is that ideally, if current is equal to the rate of change of charge, that means mathematically current I is equal to dq over dt, which is representing the change of charge. And at the same time, it is actually representing the rate of change of charge. So in a way, this is the first formula we are ever having. This is explaining the relationship between current and charge, and I'm going to number that as Formula 1. This is really important. But here's the thing. What happens, this equation is actually allowing us to find out current whenever we are given the charge. However, what would we do in a vice versa situation? What happens when we are given the equation for a current and then we are looking for the equation of charge? So that is not that hard, because what we are going to do is you're going to take the integrals of both sides, because as you can see on the right side we have a differentiation that we want to get rid of. So when you take the integrals of both sides on the right side, you're going to have I dt, which is starting from t0, which is some time, and goes up to t, which is another time. So here we have a time interval that's going to be equal to integral of dq over dt, which is going to yield a capital Q, which is going to be equal to charge. And this is going to be our second formula for charge. So Q is equal to integral of I dt from t0 to t. This is our second equation, and this is also really important, and we're going to solve some problems about this one later. So right now, I want to explain you the logic behind current in a different way, because I have seen that some students really like this one. So imagine you are having a wire, all right? Let me draw a wire in here real quick. This is the wire you have. And this wire is, of course, having a cross-sectional area like this one, all right? And let me take that in here. This is the cross-sectional area of the wire. And as we know, in order to actually make charges move, we need to connect a battery to this wire. Let's say this is the battery we have. And now charges are compelled to move within this wire, through this wire, right? So in that sense, here let me put some charges in here. So the amount of charges that passes through this cross-sectional area per unit time is called to be current. And this is another way of looking at the definition of current. Now, what I'm going to say right now is, yes, we understand the relationship between current and charge, and then we understand it, it is happening because charges flow. But there is an information that is really important, which is that we have several types of currents. You know why? Because even though you check equation 1, in which we define current as I is equal to dq over dt, we can simply say that, depending on the type of function that our charge equation has, it could be a sinusoidal, it could be like any function, right? When we take the derivative, that's just going to be our current, meaning that we could get lots of different types of currents. All right, lots of, because imagine the dq over dt equation could be anything. But throughout this course, let me just say we have a lot of types of currents, but throughout this course, let me just say current, we're going to be interested in DC currents, and DC means that you will just have a direct constant current. And then actually another one, AC, which is alternating current, which is a sinusoidal function. These are the two currents that we are interested in. But in this course, we're going to take a look at DC currents, and in the next course, which is going to be actually a sequel to this one, which is AC circuit analysis, we're going to be interested in alternating current circuits. So when we say DC current, that means you are only having a constant current, something like this. And as you can see, it is constant. It does not change. And it flows in only one direction. And when you have an AC current, that is a little bit different. As I told you before, it is more like a sinusoid. That's why you're having a function, something like this, and this is going to be your current. And I know it is tough to understand right now, but you are going to get better and better as you proceed with the course, so do not worry. And by the way, this is the topic of the next course, so just chill. And this is, by the way, moving in lots of directions. What is that supposed to mean? It changes its direction with time. So let me first put it in here. It changes direction with time. And let me show you how that happens. Basically, when you think about it, our function is moving upwards at this point and downwards in here, and upwards and downwards and upwards and downwards. See, it changes its direction with time all the time. All right, that's why it is alternating current, but DC is just a constant one. And in this course, throughout the course, we will be only interested in DC currents, and that's it. And since we are actually talking about direction of the current, let me show you something else too. Let's say you are having a wire, all right? This is the wire you have. Oh, let me delete that. This is the wire you have. And in this wire, you have a current that is flowing IA, all right? And this is the direction of IA. What would happen if I just define another current IA prime? So for a matter of fact, you know that IA is having a magnitude of 5 amperes. That's great. So can we say IA prime is having exactly the same magnitude? Or no? Yes, that is correct. They are both having exactly the same magnitude, because the thing that I'm trying to show you is that the direction of current in circuit analysis is most of the time is just a polarity matter. What is that supposed to mean? The magnitude does not change, but depending on the direction you choose, the current changes. What is that supposed to mean? IA prime is nothing but the negate of IA. All right, this is really important, because sometimes in circuit analysis, when you are given a complicated circuit, let's say they're going to ask you, find out current IC in here. And at the end of the question, you might find out between points A and B, there is a current that exists, but it flows from B to A, and it is 3 amperes. So in that case, as an answer, you don't say IC is equal to 3 amperes, but you would just say IC is equal to minus 3 amperes. This is the current that I find out, which is flowing from B to A. However, IC is not in that direction as polarity, so that's going to be minus 3 amperes. Hope what I have said right now makes perfectly sense, but if it doesn't, do not worry, because we're going to come to that one later, but I just told you to, have a quick impression on that topic. Just a little bit. And now we're going to move on with voltage, which is also really important. You know why? Because so far I have given you the relationship between charge and current, and I told you that current occurs because of the flow of charge. But one important question in here is that how the charges move. Yes, I told you that there is a battery and it compels, our charges to move, but it is not that simple. Because imagine, as a charge, we have an electron, right? And that electron needs to move from point A to point B. And how is that going to happen? It is not that easy, because we're going to require some energy. And that is really important. And that energy is, by the way, provided by an external source, which is called electromotive force. Electromotive force. And this force is generally shortened as EMF, or sometimes it is called voltage, and sometimes it is called potential difference. So, how do we define that voltage or potential difference? Let me put it this way. Potential difference is defined as the energy that is needed to move a unit charge from point B to point A. So, let me put that in here. So, in a way, we can put this mathematically. You know why? Because from point A to B, V, by the way, represent our voltage as V. VAB is going to be equal to, the work in here, let's say, is omega, all right? So dW, this is not omega, by the way, sorry, this is W, dW over dQ. You know why? Because this is actually indicating that we are looking for the amount of energy that is actually needed to move unit charge, and this is the third formula we are having, which is the formula of voltage, and that's also really important. So right at this point, there's something that I want to tell you, which is that when you have a circuit element, all right, let me draw one. This is the circuit element you have, and it has 2 terminals, right? A and B. So the definition of voltage is all about polarity. That's really important. We have talked about it about current. We have talked about the polarity that the current has. But this one is a lot more important. I don't want to say a lot more important, but this is, as much as important as it was, as current was. So polarity really matters in here. Because what we do in here is basically this. So we are looking for VAB, right? And VAB is obtained in a way, this plus and minus is reflecting our polarity. VAB is equal to V plus, meaning that the plus side of the polarity minus V minus. And this is the minus sign of the polarity. This is the positive part of the polarity. And I will give you a really good example right now. Let's say we have VA, right? One side as 9 volts. And then we have VB, the other side, as 18 volts. So in the first case, let's say this is the circuit element you have, plus minus, this is the polarity, be careful, and we are looking for VAB, and this point is A, and this point is B. Then how do we calculate the voltage across this element? So I'm just simply gonna say that VAB is gonna be equal to V plus side minus V minus side. So the plus side of the polarity represents VA, so that is gonna be 9 volts, minus the negative part is representing point B, so that's 18 volts, so minus 18. In the end, I'm going to have minus 9 volts. But in other way around, when we have again exactly the same circuit element, and this time the polarity is not like the one above, but this time it is reversed. So in that case, we're going to have minus VAB plus. And in this case, what I'm going to say is VAB is going to be equal to V plus minus V minus. And this time plus side is referring to point B. So 18 minus 9, it's going to be 9 volts. And as you can see, polarity does not change the magnitude. It only changes the direction. So this is like really important. And now our discussion on voltage is ended. Now it is time to talk about power. So power is another important thing. Because basically, it's like one of the most important things, because imagine, you have the voltage and current, but they're like workers. The main idea in here is power and energy, because in the first lecture, I told you that we are transferring energy from one point to another, so we are basically interested in that one. Voltage and current, they're like tools that we help us to find out the power and energy. So power is basically the time rate of absorbed energy, logical. And it has an SI unit of watts. And in order to put this particular sentence into mathematical equation, it does not require too much math. P, which is power, is going to be equal to dW, which is energy, over, since we're talking about time, they're going to find out the energy that is absorbed per time. So dW over dt, which is going to be the equation for power, equation 4. And right now, actually, we are going to have an enlightenment. What is that supposed to mean? Let me remind you the fact that voltage is equal to dW over dQ, meaning that we are looking for the energy needed in order to move a unit charge. And then we know for a fact current is equal to dQ over dt, which is the amount of charge, per unit time. So what happens if I just multiply current by voltage? In that case, dW over dQ times dQ over dt. In the end, we are ending up with dW over dt, which is exactly the same equation as power. So now that means we are coming up with another equation. Let me put it in here. Power is equal to voltage times current, and this is really important. And this is, let's say, equation 5. So after this point about power, we have found out 2 equations that are really helpful. Another thing about power is that sometimes an element can absorb power, and sometimes an element can supply power. Because when you think about it, imagine you have a battery. That does not supply, that does not absorb power, it supplies it. So how to understand if an element absorbs or delivers the power? So basically, there is, 2 options. Let's say we have a power across the element. It can be either absorbed or it could be also supplied by the element. So when that's the case, if the power that you calculate for that particular element is positive, then that means power is absorbed. But if the power is negative, then that means the power is supplied. So how is that going to happen? I will explain it a little bit more. But how to understand if power is I mean, positive or negative, what is that supposed to mean? I mean, I'm just going to multiply the current with voltage and then it's going to be, I mean, a numerical value. I mean, how do you come up with the idea that power could be negative or positive? Let me explain you. So here's the thing. If current enters your element from the positive terminal of the element, then power is absorbed. Let me put it in here. I know this sounds a little bit abstract, but I will give you 4 examples. Let me take my time to draw 4 different circuit elements. So here's the thing. For the first element, as you can see, current enters from the positive terminal to the element. That means current is absorbed. So power is going to be, power is absorbed. So power is going to be 3 times 4, which is 12 watts, and power is absorbed. But in here, current, as you can see, I mean, follow the path. As you can see, it enters from the negative terminal. So that means power is going to be equal to 4 times minus 3, which is minus 12 watts. And that means this particular element supplies the power, which is very nice. And then here, current enters again from the negative terminal. That means power is going to be 4 times minus 3, and again it is minus 12 watts, meaning that again this particular element supplies the power. And in the last example, as you follow the path, current enters from the positive terminal. So what I'm going to say is power is going to be 4 times 3, which is 12 watts. So the power is absorbed by this particular element, and this is the logic we have in the absorption or supply of the power. So power is done, I guess. I mean, yes, there are more concepts that we are gonna find out, but that's for later. So for now, it is sufficient enough. And now there's wait. There's one thing that I want to tell you. There is the law of conservation of energy, right? So that also must be obeyed in electrical circuits. So what is that supposed to mean? In an electric circuit, the sum of all the powers must be equal to 0, meaning that the supplied power must be equal to the amount of power that is absorbed. So these 2 are really important. Just keep them in mind. So there's one final thing that I want to mention, which is energy. That is also really important, but I'm just going to give you a little rough idea, because I know this video has been really long, but you really had to learn these concepts. So here's the thing. Energy is simply coming from power. When you think about it, we define power in a way that it is actually the amount of energy that is absorbed per time. So power is dW over dt. And in this equation, if you take integrals of both sides, you're going to find out power dt, which is the integral of power between a certain interval. Then that's going to be equal to energy. And this is the formula for energy, probably equation 6. I don't really recall. Let's check. So yeah, it is 6. But let me also say this is equation 7. That's also really important. So if you want me to, define energy, I would say it is capacity to do work. That's also really important. So let me also put that in here and end this lecture. Alright, so in this lecture we have covered nearly all the basic concepts about electrical engineering, and I think it was a really useful lecture. I don't know, in the editing parts my friends would probably warn me about the length of the video. If the video is really long, then we would cut it off, 2 pieces. Then, do not worry. I don't want you to deal with like a 40 minutes of lecture. If you want to, deal with the 40 minutes of lecture, you would just go to school, but you are looking for online solutions. So that should be shorter, right? So thank you for watching this video, and I apologize sincerely that it took me this amount of time to explain you the basic concepts. So in the next video, we are probably going to be talking about another basic concept video, nodes, branches and stuff, loops in the circuit. So see you in that one. And again, thank you for watching. If you have any questions, please do not hesitate to ask. I'm always here to help you out.